ML data input. So in order to do to get ready for the machine learning, we have to generate, as I mentioned here in the slide, we need to generate, let's say, a buttonhole pressure as a function of all these variables. So what we're going to do is generate a data frame, which I'm going to call X, and it's a sort of a accepted nomenclature. And I'm going to take all these train wells. I'm going to take only the data for the train wells. And in X, I'm going to store all the columns that I'm going to store in X are going to be the predictors. So essentially what I'm getting is to a point where I want to use only the variables or that I consider that are influential to the buttonhole pressure, okay? And as you can see, obviously, I'm not introducing anything that is related to the buttonhole assembly, such as the buttonhole temperature or the buttonhole pressure itself, because we want to predict those, or we want to predict, in this case, only the buttonhole pressure. But I'm dropping the buttonhole temperature because I am going to assume that we don't have any sensor in the bottom. So I don't want to get that information. I don't want to use that particular information. Okay. And the other thing that I'm going to do is I'm going to do Y. And my Y is what is it that I want to predict? Yes. So this is going back to the function. This is my Y. This is my buttonhole pressure. Of course, we can have many Ys. We can have many things that we would like to predict. I could have gone for the buttonhole temperature as well. But let's go for the buttonhole pressure. And in this case, it's the F training wells. And I'm going to take only the buttonhole pressure, okay? So if I run that, and if I show you x.info, so x.info or x.info has only these variables: DP tubing, tubing head temperature, tubing head pressure, choke size. I remove dates because I'm not going to use dates as a predictor. I'm assuming that the behavior of a well in a particular moment is independent of the behavior of a well 2 days before, and so of course we can argue that that may not be the reality, especially if you have something like an equipment like an electrosubmersible pump, where you are trying to predict if a pump is going to fail. Of course, a failure of a pump is going to be affected by what's happening on the previous days. But in this case, I'm going to make a simpler model. I'm not going to, well, it's not simple, but I'm not going to assume that the time is a variable to be considered. And so we have that. And the other thing that we need to do is use the key library to use machine learning. So, of course, I talk about linear regression, decision tree, and some of these techniques. But if we think about how to perform machine learning, there are in Python two techniques that we broadly, there are several libraries in Python that we can use for machine learning. But let's talk about probably the two the most important libraries. Of course, with black, it won't describe anything. So Python libraries for machine learning. So one, and I think that this is the most common one that is has evolved quite a bit, and so it's scikit-learn, and also called sklearn. And this is mainly for supervised and unsupervised learning. and also regression and classification models. And it also has some pre-processing tool. So in pre-processing, you can do some interesting things like data split, which we'll see in a second. We could do also things like standardization. We can extract metrics of the models, etc. And the library number 2, it's there are other libraries, as I mentioned, but the other one is TensorFlow. And TensorFlow, it's mainly for artificial neural networks, and that's it. So that's what we're going to be focused. So we're going to focus at the beginning, or I think due to the time we might be able to just scikit-learn, but let's see how far we go. But going back to that image that we have on the slides, this is all this part of the all this part of the information, all this part of the slide. We will use scikit-learn, and for this particular one, we can use TensorFlow. Okay. Let's go back to the plot. Okay. To the exercise. So we're going to import scikit-learn. And the first thing that I'm going to do is use a feature called model selection. And with this, I'm going to do what is called a train test split. Very quickly explaining what is a train test split. Let's say that you have all your data. Yes, this is all your data. And what we would like to do is split the data into a train and test. So when we run a model, let's say we have what is called the X. Yes, all those variables that are here, all these columns that are here, which are oil volume, all the columns that we spoke before, oil volume, the choke size, all those columns. And we have a Y here, which in this case is a bottom hole pressure. Okay, so we're going to have also a Y, a series of values. And we're going to have the X train, X test, Y train, and Y test. Why do we want to have that? Because we want to train the model. We want to run the ML training, call it training or call it training or fit, using only the train data. So this will produce a metrics such as, let's say, the R square or the root mean square error or the mean square error, whatever metric you have to come up with the quality of a model, which ultimately will tell you, let's say you have here your train data. But ultimately, that metric is going to tell you, let's say you produce a model and you have the real values. And when I call real values, these are, let's say, the real BHP values, and these are the predicted ones. And you know that these more or less have to be aligned to a 45 degrees or to a straight line. So there might be points that are here, here, here. And these points that are here are very basically telling you that you know that the bottom hole pressure should be this much, and you're predicting this is much, okay? So in training, we can reduce very quickly the model quality. So this is model quality, these metrics here that I put here. But we need to test the same thing. So we have a real values, and the predicted values on the test data. The test data has not been trained. I'm not using the test data to train. So what would happen there is that this will have a bit more of dispersion. Usually will have a bit more of dispersion. So when you try to predict there, you will have more dispersion. So we can say, for instance, this is an R square. We can say, for instance, that my root mean square of a training is greater than my root mean square error of a test. But what is important is actually this part of this quality is the important one, because this is what will tell you if a model has good quality or bad quality. And usually what we do is take a 20, well, depending on the amount of data, but usually you can do with 15% to 30% of test data. Okay, so let's do that. I'm going to train split, and I'm just gonna type here. I'm gonna take the training data, test data. Let me write the function. So I'm gonna take the train test split, and if we see the, sorry, I need to run this. So if we see the train test split, we have to put the test size, which is what is a fraction, in this case, a 50 to 30% that I mentioned before. And something that is called a random state is to make sure that we can repeat the exercise and still have the same matrix. Okay. And as you can see in this example, what you have, and let me copy exactly all this.
Alejandro.
Yes.
In this case, since you're predicting, like you have three wells for training and 2 wells for tests, right?
Wouldn't it be, yes, yeah.
Wouldn't it be, sorry.
Yes, carry on.
Yeah, wouldn't it be better to have like a complete well as a test, just so that we don't have any data leak?
Yes, absolutely. I mean, no, I don't think this would be related to the data leak, but if from the point of view of what we're trying to achieve, let's say you're absolutely right. I could you can take, let's imagine that we have 5 wells, and going back to the slide, we can assume that my train data is 60%, so 3 wells. And my test data is 40%, 2 wells. But at the same time, I want to be a bit more rigid on one well, and check on one particular well how the model it is. And the other reason why we did it this way is that we weren't quite sure if we were able to extrapolate the training data from one well to the other because of a well deviation and all that. So when we prepare the model the first time, we say, well, let's do the train test split on a well by well basis, and assume that you can only predict on a well if you have information. But later on, we realized that the model was, and we'll show you, the model was good enough to train in 2 wells. It's like what you will do in petrophysics. You will train you will train based on 2 or 3 wells that the petrophysicists have done, and then you will test with another well. You're absolutely right.
That takes us, Alejandro and Mr. Yasser, that takes us to the concept of the blind well test, where you completely hide one well from the model, or the post-mortem analysis, which we refer to it as validation, where
Yes.
there was no well at the very beginning of the drilling. Then they drilled one well. Then you apply that model to the newly drilled well. So
Yes.
we are now, which one usually will be more accurate? It's again, precision, not accuracy for the model. Applying it to one well that was part of the cluster versus applying it to, I mean, it's blind well test versus the validation test.
Yes,
That's what I'm
yes.
saying.
Yes, exactly. That's a similar concept that I'm trying to apply here with the wells to fit. Yes, as you can see, I'm training only with 2 wells. So the other wells are blind to me. The other wells, I'm going to base on the other wells. But as Yasir mentioned, we also have blind data within the well. That whether we might not be, we may not need to do this step, but I'm going to do it for the sake of going comprehensively through the process. But you both are going into the right direction. So if I do that, and now I have 20% of the data is test data, and I have this random state, and I'll show you why we need the random state. Let's say that I run this without the random state, and I do X train, and let me show you first the header. Yes, so you see all these values. My rows are 829. So if I run this again, I will have a completely different sampling. But if I put a random state here, I'm fixing it to a number. That number could be whatever number you want. You can be 1. It's what is equivalent in geostatistics to a seed, instead where statistics to a seed. So if I do 1 there and I run it, 1794, and I run it again, 1794, I'm making sure that my split is always the same. So in order to be to have a reproducible workflow, this is recommended. Okay. And now you can also see that my X underscore train, the shape of the data is, this is a shape of the data, and the test dot shape, shape again, is this. So we have only 20% of the data in the test and 80% of the data in the train.